Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Introduce Aman Kansal. Aman is a PhD candidate in the Electrical Engineering Department of UCLA. Over the last 4 years at UCLA, he worked on a number of different embedded systems projects where he had to develop algorithms and build software systems and hardware platforms. And his current focus is on mobile sensors with a special focus on controlling uncertainty in sensing and communication. With that, Aman.
Thank you so much.
Sure.
So today I'm going to talk about how we can use motion for reducing the uncertainty in the data collected by a sense network. And this is one of the problems that I've been working on. Sensing performance is the key theme here. There are a lot of problems in network and embedded sense networks today, networking being one that to some extent there are first order solutions. It's not a solved problem though. There are problems in processing the data coming. And there's of course this problem that I'm going to address today. I've looked at sensing performance in 3 different projects. The first one I'll talk about today, how we can use motion to reduce the uncertainty in the data that we collect. That is using motion. There are other ways to do that as well. For instance, we can collaborate among multiple sensors and hence give a lower uncertainty in the fused data. I'll just refer you to the publications for that. And another project where we want to collect more data, and to do that using the wireless bandwidth, we do some processing on the end node itself so that the amount of data being transmitted out over the wireless links is reduced. Again, I won't talk about that today, but I can give you references if you're interested. So for the first problem, we're trying to use motion to reduce sensing uncertainty. Why motion? When people have used motion for wireless networks in different ways, it was shown early in 2000 and later in 2002 in a more formal way that wireless networks help improve the capacity motion helps improve the capacity in a wireless network. Motion also helps improve other things, for instance, for security, for localization. I'm sure some of the people know this work. Then for routing. And this is using random motion. There are wireless nodes which people are carrying, moving around with them, or maybe mounted on randomly moving objects. Now in sense networks, we have the option to use controlled motion. That is, we can control how the nodes move, because sensor nodes are not necessarily nodes carried by humans. And people have built prototypes of sensor nodes which are mobile. I've just put a couple of pictures in a few pictures. There are a lot of others too, and these are by no means like the best ones or anything. So for using motion in sensor networks, I've again worked on a bunch of problems. First one is for improving the sensing performance. And this is what I'll talk about in more detail today. This picture just shows a prototype. And here we use a particular form of motion, what I call small motion, and I'll come to that. Second one was using motion for communications. Here, it might sound counterintuitive, but in some situations it happens that carrying the data on a robot rather than transmitting it wirelessly is advantageous in terms of the energy spent by the network, the total energy spent by the network on motion as well as on communication. So I won't go into the details, but we had a prototype implemented for this, and I can refer you to the publications. A third one, this is an application. Using motion, using mobile sense networks for an exciting applications. This is a fun application in particular, entertainment kind of stuff. If you are aware of games like Age of Empires or Warcraft, this is something which allows you to play a similar game in the real world using robots rather than in the computer. So, and this had a lot of other students collaborating as well. And what we built was this little robot and a 3-dimensional terrain on which these robots run. The robots have a lot of their navigational sensors, but in addition they also have application-specific sensors such as a CMOS camera and an RFID reader, which we use to simulate the gaming aspects. And this terrain itself, it's a 3-dimensional thing about 10 feet by 10 feet with mountains, rivers, and that kind of stuff. And it's reconfigurable. It has certain elements which we can control electrically. We can send them signals and things will change their shapes. For instance, say a robot can destroy a particular object in the scene, or certain pathways may be opened by doing certain things. So this was another use of mobility. A fourth one is where we use motion to achieve something which is almost impossible with a static sense network. Here, for instance, what you see in this graph is the nitrate concentration across the cross-section of a river. And this is taken at 0.5 meter resolution along the horizontal axis, at 0.1 meter resolution along the vertical axis. Doing that with a static sense network means you deploy sensors at that high resolution across the river cross-section. When doing that is not only costly and bulky, but it will also interfere with the flow of the river itself. What we are doing here is using the system to suspend a sensor node, a single sensor node, and move it along this cross-section in the 2D plane. This motion is not as hard as a fully autonomous robotic motion because the motion is supported by this cable infrastructure. But what it does allow is getting this high-resolution data with in a much simpler manner than with a static network of that many sensors. So that was showing a few different ways in which I've used motion for sense networks. What I'll talk about today is how we can use motion for improving sensing uncertainty. And in the particular prototype hardware that I'll show, there's a potentially an advantage of 15,000 times improvement of using motion. Of course, there are trade-offs which I'll talk about. So we'll begin with those trade-offs. And then I'll show a system architecture that allows systematically using the motion capabilities. Then we come to the actual algorithm, which I've developed for using that motion. And finally, we'll evaluate the stuff. So why do we want to use motion? Motion can help improve sensing in at least 3 ways. One is, consider the scene, say a shopping mall or some railway station where there are a lot of people present. And we want to take an image of the entire scene, entire 3D volume, at such a resolution so that we can recognize the person present there. So let's just suppose recognizing a person means that the 1 centimeter in space should map to 1 pixel in the image. Let's say the way our recognition algorithm works needs this resolution. Then one option obviously is to deploy enough sensors that the entire 3D volume is covered at that resolution. The other way is that wherever the faces or the phenomenon of interest is present, those regions are covered at that resolution, while the remaining area is covered at a low resolution, just enough to detect where the phenomenon of interest is present. So that's one way in which motion can help. We can detect at low resolution and selectively focus our high resolution sensing at the regions of interest. A second way is there might be obstacles in the medium. Any realistic deployment environment would have obstacles to the field of view of the sensors, and we can use motion to adapt to those. A third way is, of course, a mobile sensor can cover more area by just moving from one place to the other, and this is something which has already been exploited in some other projects. Today I'll focus on mainly the first way in which motion helps, to a little extent the second way as well, not using the third way, which is essentially a moving sensor covering more areas at different points in its path. So first question is, of course, do we want to use mobility or do we want to use a high density of static sensor nodes? These are definitely two alternatives. And there's also a third alternative, which I'll show is very interesting. That is, we can use a density higher than the density required with mobile nodes, but each node has only small amount of motion. Why small amount of motion? Because, and by small amount of motion here, I mean such a capability such as pan, tilt, and zoom in a camera, or motion along a cable, the kind I showed in one of the projects. So why this kind of motion? Obvious reasons. One is it's much easier to navigate for such motion than a fully autonomous robot trying to navigate in a 3D terrain. Second reason, the energy requirements are much lower. We don't need to move the bulky parts like the motors or the batteries in the node. Only the transducer part of the node has to move. Third reason, which might be important for some applications, is if the sensor is a high bandwidth sensor, for instance a video camera, we might need wired access to network the camera. And providing wired access to a node which is moving freely in a 3D world is much harder than providing it to something which just has pan, tilt, and zoom capabilities, but stays in the same place. Fourth advantage might be important in certain environments, that is, the intrusion into the user space is minimal if the node sticks to its location using, say, only pan, tilt, and zoom, but doesn't move like a robot does. So those are the intuitive arguments. Now let's evaluate more quantitatively for a particular hardware choice. This is the camera I use in my prototype hardware. It has pan, tilt, and zoom built in. It's a network camera. Let's just try to model how much we can get if we allow pan, tilt, and zoom in the network. So this pyramid here shows the volume of space covered by the camera from one pose. And the range here, the distance up to which the camera can sense, essentially comes from the resolution desired in space. So this is a pyramidal shape of volume covered. Now let's say we allow the camera to tilt, use its tilt capability, then this figure shows the volume swept out. And similarly, we can combine pan, zoom, and sort of do the volumetric calculations to compute the volume covered with the motion capabilities. These are the numbers for that particular hardware that I just showed. And it seems that with all these pan, tilt, and zoom, we are getting about 5 orders of magnitude increase in the volume. Now that's the potential of using this small motion. How much of it can we realize in a realistic setting? Oh, so these numbers are, say this number here is a ratio of the volume covered when the camera can use its pan capability to the volume covered without the pan capability, just the static. So this volume this volume with tilt divided by just the static volume would give me this number. So, and the final number is, of course, with all the three capabilities combined. So that was the total potential. In a realistic setting, how much can we realize out of that? At least one way to use that motion is I use low resolution to detect, and then wherever I detect something, I zoom the camera in. So now this might not exploit the entire zoom or the entire pan capability, because for instance here, my detection, the field of view for detection is limited to a particular angle. My pan beyond that range is going waste, even though the camera has it. Same for zoom. Even though the camera might have a zoom of 25 times, but the difference between the resolution required for detection and the actual sensing task might only be 5 times, and then I can use only 5 times of the zoom. So, and there might be a constraint on the delay. After detecting, I might have to zoom in to the region of interest within a particular delay, and that might limit the amount of motion I can use. So with these more practical constraints, this graph shows the calculated advantage in volume covered for different choices of the tolerable delays and the zoom factors. For instance, at about 1 second of tolerable delay with the particular hardware I showed, we can get about an order of magnitude advantage in the volume covered. And of course, if we allow a little more delays at 2.5 seconds, we can exploit up to 15,000 times of the advantage in volume covered. It's still not going to the full 200,000 times advantage, because we can only detect in a small part of the entire volume. Now, if we had some other mechanism to use this capability, that is, we detect using some other sensors, an acoustic array which detected the presence of a sound source, and then the camera was to zoom in, maybe we could exploit the entire 200,000 times advantage. But this is just still showing that there is enough promise. Question?
By motion delay, do you mean the time it takes to span the whole region that you're talking about?
No, by motion delay here I mean after I detect something, how long does it take from any point where the camera may be looking to zoom into that point? So it's a single step, not the entire raster scan.
So you're assuming a reasonably static environment when you do this. So you get no temporary.
Static in the sense that after I detect, within this delay I have to zoom into that point. So the environment has to be static, and for how long the environment is static will govern this tolerable delay I have for actuation. Right.
That's a pretty big assumption, right? Like it's moving people.
Right, but here our tolerable delays are also of the order of seconds, and if we are using, say, photographing a moving person, we might just zoom into an area surrounding the person's face so that he will be within that region for, say, 1 second. So yeah, there is definitely an assumption, and that's the key trade-off which we will have to handle when designing the motion control strategy. So that was the advantage for a single node. If we have a network of nodes, of course for each node we have the advantage that was for the single node, but we can also expect some additional advantages in a network. One is, compared to a static network, a mobile network can reconfigure its orientations for the cameras, for instance, in a pan, tilt, and zoom setting. to minimize overlap among sensor nodes. Also, if there are obstacles in the medium, we can overcome those using the small motion, to the extent possible using the small motion. Now, I'm not going to analyze it because it really depends on the kind of environment, the nature of obstacles in that. Just to get intuition into the kind of advantage feasible, I'll simulate for multiple random configurations, multiple possible obstacle placements in the environment, just to see if there is any advantage along this dimension. And we'll compare static nodes, nodes with just span capability, and nodes which are fully mobile. Question? Oh, sorry. So this graph shows the density required for the same coverage using different kinds of motion. So obviously, if the node is fully mobile, we need a much lower density. In the ideal case, even one mobile node is enough to cover the entire region of coverage. The reason why we still have like a number greater than 1 here in this graph is I put a limit on the delay tolerable. So I'm comparing all the capabilities at the same tolerable delay. The pan nodes obviously save a lot. This is a log scale, so these differences are significant here in density. Compared to the static nodes, for instance, the nodes with pan only can save about 7 times in density. So it seems from this analysis that there is sufficient motivation to use the small motion compared to a high density of static nodes or fully mobile robotic motion. So, of course, this was just a graph comparing the densities. One might claim that a mobile node is costlier than a static node, and what's the total cost of the network? That's what one should compare. Now, I've done this comparison in this graph for one particular case at 90% coverage. And these numbers, of course, are highly technology dependent, the kind of hardware I used for the cost analysis available at this particular time. Here, for the static and the pan-only case, it's the same camera from the same manufacturer, one which comes without the pan zoom and tilt capabilities, and the other which comes with the pan zoom and tilt capabilities. The linear case, I assumed the same camera, but our own hardware to make it move along along a one-dimensional track. For the fully mobile case, it's really hard to get the numbers because the robots that one can buy off the shelf do not have the navigation capabilities built in. What one can get is just a traction platform that can move around. One has to put in the hardware and the software to control it. So I have not put in that cost. And even among these traction platforms, the cost varies. If it's a robot, we can just move on flat surface, or if it can move on somewhat more rugged surface. So even without the cost of the navigation hardware and software, the cost for the fully mobile case seems pretty high. If we add those components, it seems that the nodes with limited motion are probably the ones which are going to win. So, okay, assuming that we are convinced that we are going to use small motion to improve our sensing performance, how should we do that? The first problem, of course, is this. We have a network of cameras. Each node has various pan, tilt, and zoom settings. What particular setting should it use in the network so that the overall sensing performance is optimized? And I'll define a metric to govern what optimum is. A lot of people have worked on problems for controlling the motion of mobile nodes for different for different problems. One for the deployment phase itself, where the node should be placed. Say the art gallery problem, where the goal is to find a deployment of the sensor such that the entire polygon region given is covered. And these are typically solved in a centralized fashion. And there are other problems. I'm not going into each of these, but there are essentially solutions to solve the motion problem for different objectives, not the particular objective that I'm going to talk about. So let me show an architecture for the system to solve the particular problem that I'm talking about. Here we'll assume that, I'll just divide it into these tasks, that we have some mechanism to learn about the obstacles in the medium, some mechanism to learn about which areas in the total area that we're trying to cover tend to have more events occurring, more phenomenon of interest. And this information is given to our algorithm which will control the motion, and that algorithm will actually decide how the sensors should be oriented depending on the kind of motion capabilities that we have. And for the first two blocks, I won't discuss exactly how we implement those. I'll just give you examples of what I did for my prototype, a very brief description here. So what I did was use the laser ranging device to map the environment. There are other ways to do this. For instance, use a single photon detector to get a 3D image of the view, or use stereo vision when feasible. But I just used a laser device to scan the entire region, get a map of the obstacles. Again, the reference gives how exactly this is done and how the data among multiple lasers is shared. The second part, learning where the events occur. There are several ways, again, to detect phenomenon. For instance, two that I have implemented for a couple of demos that I gave for the system. One was to use color detection. The application was that there are smart objects in our space, or it's a smart computing environment where the objects are tagged with this kind of a visual tag. Now, there are off-the-shelf algorithms available to recognize this tag. This tag is like a barcode. It has an ID. This pattern corresponds to a particular ID. So those algorithms can convert this pattern into the ID, given that you have a good image of the tag. So the application is that we want to get high-resolution images of this tag, of these tags, and we use color to detect that. So color detection in that case can be used to build a map of where events tend to occur. The second example is we use motion. For instance, we want to photograph vehicles entering, say, our building from a particular exit point. Then we can use motion to detect where the vehicles are, and we would then focus on those regions. But to build a distribution of where the events occur, we can just use motion detection. Just a couple of examples. Today we'll just assume that these are available to us. And what we'll talk about is this motion coordination algorithm itself. Now, people have worked on the motion coordination problem for coverage for for somewhat different problems, not exactly the stuff I'm talking about. A key distinction being these algorithms, which I've listed out here, do not account for the delay taken in motion. These are one-time optimizations, sometimes solved centrally, sometimes in a distributed manner, for finding out how the network should be configured. I'll describe the optimization metric that I use, and that accounts for the motion delay, which is very crucial here because we are comparing against a static network of deploying much higher density of sensors to get the same coverage. So before I describe the motion control algorithm, let me clarify that there are two phases to this motion control in this situation. One is we want to optimize the configuration of the network a priori before any events happen, so that the time it will take us to move when an event happens is minimized and the area covered for detecting events is optimized. The second phase is what I call the reactive phase, is when an event occurs, one camera or multiple cameras would have to zoom in to that particular event. So what I'm solving is the first part of the problem. Okay.
So in your system, do you have the same cameras doing both? It seems like you might want to have one kind of large-scale camera that's always watching the entire
Exactly. So you can view the solution I'm giving in two ways. One is the solution is applicable to that network which is doing the detection, and a second network of more focused cameras would do the sensing task. Or it could be the same network doing the detection. Yeah, when something is detected, it will zoom in and lose the detection capability for the time. So it really depends on how you're solving the second phase, using separate cameras or the same cameras. My solution is for the first phase. So here there are two things that we want to model in our optimization metric. One is the time it takes to zoom in after detection, and I just call that motion delay. And a good configuration of our sense network will minimize the motion delay regardless of where the event happens in our field of view. So to model this motion delay, all we need to know is the time it takes for the pan, tilt, and zoom motions for the camera to zoom into a particular point. The pan and tilt is easy to model because it's almost linearly related to the angle one needs to turn. The zoom is a little more complicated because the way the zoom mechanism in the camera is built, it's not linear. Going from zoom 1 to zoom 2 doesn't take the same amount of time as going from, say, zoom 5 to zoom 6. So I just experimentally measured it. This curve gives that graph. And we feed this actual nonlinear data into our metric. So we are not making any assumptions about linearity on our optimization metric here. Second is the amount of area covered and the quality of detection we are getting. Now this quality would depend, depending on the application, on the distance from the camera. Something closer to the camera is likely to get detected better. It will also depend on the line of sight. If there's an obstacle in the middle that will block line of sight, obviously we lose detection capability. Again, here we have this metric which could be evaluated in a very empirical manner for a particular environment based on the line of sight data that we have from the lasers. And we are not making any assumptions on the continuity or the smoothness of this metric. So these two things govern our sensing performance. And to get a single metric, I'll just combine these with a weighted sum where W is a number between 1 and 0. And these weights could depend on the application, or we might just want to optimize for one of the metrics, say the motion delay, and not even worry about the area, or just worry about the area if delay is not a big consideration. The other question? Sorry. The other thing which I said we might have information about is which regions in the area of coverage tend to have more events occurring. And if we have that information, I'll just denote it by QP. P is a point in space, and Q is the distribution over all points in space for the events occurring. We'll just weight this metric, F, which is the sensing performance metric, by this event distribution. And finally denote our optimization metric, U. We'll just call it the sensing utility for the network. UP is defined at a point in space, and I'll just take a sum over all points in space to get the metric for the entire network. Now this capital U is hence the sensing performance metric for the network as a whole. Depends on the configuration of each sensor, each camera in the network. And what we want to do is optimize this, maximize this utility to get a good quality configuration. That is, the correct pan, zoom, and tilt setting at each camera should be chosen so that this metric is optimized. And now it can be shown that this is a NP-hard problem. Second, which obviously means that we need a good solution which can work with the combinatorial complexity of the problem. Second is, this is a distributed system where the information that we are getting, the information about the obstacles which are used to get the coverage quality, the metric CP which I showed earlier, and information about the event distribution, that might be available in a distributed manner. That is, nodes within their covering a particular area may know these things for their particular area. Obviously, these can be exchanged to a central server, but it might be nicer to have a distributed method to do that. So I'll try to design a distributed solution to this optimization problem. Here we are searching over the question.
Do you see having to solve this optimization problem at every instant in time? So you're dynamically controlling the 3 parameters for each camera?
Not really. We are solving this configuration problem once, and then when events occur, a different algorithm will be used to zoom into those events. This is a solution that is required each time the environment is kind of changing in some sense. So let me just say the environment is static, then we need to solve this problem just once. Now we'll solve it again when we think that the event distribution that we learned over space has changed, or we'll solve it again when we think that the map of obstacles has changed.
Gotcha. So here you've set down n cameras, and you just you're having them in kind of the monitoring mode,
right?
The vigilant mode,
right.
But not the zoomed in to detect to
right.
recognize the event mode.
And optimizing this will cause this configuration, the monitoring configuration, to be such that when something happens, my delay to zoom in would be small,
Gotcha.
and I'll have a large area over which I can detect. So to do this optimization, let me try to write this utility metric US in a distributed manner. The first obvious way to do that is to divide the area A over which the coverage is into smaller subsets which are affected by unique sets of sensors. For instance, just take an example with 3 cameras, 1, 2, and 3, and this greenish region shows what area is covered right now. Then I can just see here which area depends on which sensors. For instance, this area B2, which is this shape, depends only on sensor 2. This area, let's say B7, depends on all the 3 sensors. This area, this little thing B5 here, depends on sensors 2 and 3, and so on. So, and each of, just the reason why I wrote it this way is each of these areas, the sub-areas B, B1, B2, is disjoint from the other in the sense that the set of sensors affecting it is unique. And I can hence write the utility metric as a summation over these little areas. For all points in a region, we can calculate the utility metric without worrying about the other regions.
Question here. Maybe I just missed this in your formulation of your cost, but I don't see how you're accounting, or I mean, you're talking about this right now, but how you're accounting or discounting for the fact that how many sensors are covering a particular area, or, I mean, for instance, like, there could be a pathology in your cost metric where if multiple sensors are all covering the same spot, right, there's two ways in which you can have a problem with that. One is that you count them both as good because they're covering an area that you care about that has a high QP.
I think I forgot to mention that for a particular point where two cameras are covering it or more than one camera is covering it essentially, I take the coverage dependent on the camera covering it best.
I see.
Yeah, there are other ways to aggregate. Maybe for some applications, if two cameras are covering it, it might be better than one camera, and we may design the metric in that manner. Question?
In your figure, it looks like you've arbitrarily truncated the ranges.
Oh, you mean the camera has a range only up to this point?
You can't do that in real life, necessarily.
That range is dependent on the resolution required. So depending on the distance from the camera, a point in space will correspond to a certain number of pixels. So if we want, say, 1 centimeter square of space to correspond to 1 pixel in the image, there will only be a certain range up to which the camera is sensing. Of course, in the image, we'll see areas beyond it, but we are just saying that any event that occurs beyond this range won't be detected, because it will occur at such a small resolution that the camera won't be able to detect it. So that is why the range is getting truncated.
I don't know how you can delineate when you're monitoring that.
Oh no, I mean, the camera will get an image of the entire field of view. So if there is, for instance, this is just open space and there is no wall at this particular distance, the camera will probably get an image of something behind it. But what I'm saying is that for the purpose of the calculation of the coverage, the range is only up to this point, because if an event occurred beyond this point, it will not have been detected by the camera. Because
it means being able to recognize the face,
or
not just see some stuff in the camera. Yeah.
Right. Say we are detecting an event, say a face based on
False, like a picture of a large picture of a person's face in the background. That could be a false detection, right?
Yeah.
Right. If it's a large picture, yes. Yeah, those cases can occur. So this is not saying that the camera is not getting an image of the things behind this range. They're just saying that for the purpose of calculation of coverage, we are assuming this area is covered, something behind it is not. The detection algorithm itself may have false positives or so on. So this was just one simple way to divide the area into disjoint regions. The problem with this way is that the number of these subregions is exponential in n, and what I'll do is modify this distributed expression slightly so that this number is no longer exponential. To do that, let's say this. For each sensor I, let's say sensor 2, let's find out the set of sensors which have overlapping regions with it. For instance, for sensor 2, sensors 1 and 3 have some point which overlaps. Not necessarily the entire region covered by sensor 2, but some point within the influence of sensor 2. So let me just denote that subset of sensors which have some overlap with sensor 2 as gamma I. So what this, knowing this gamma I enables me to, at sensor 2 I can calculate the coverage, knowing only the positions of the sensors within the subset gamma I. I don't need to know how the remaining network is configured. In this example, of course, it's the entire network, but let's say it was a big network, this is just a small portion of it. So what I'll use this is to write the utility metric as, again, a distributed expression, but in terms of these subsets, the capital gamma i's. This capital gamma I is the region where, depending on the poses of sensors, say 1 and 3, sensor 2 has calculated the sub-region where sensor 2 is responsible. That is, within this entire region covered by sensor 2, what parts of it are the ones where sensor 2 has the best coverage? It will definitely be the region B2 and maybe some portions of the other regions. So that the total region I'm denoting with this capital gamma I, and I'm then writing this utility metric as a summation over these capital gamma I. This is again a distributed expression in the sense that to evaluate this utility over a particular subregion gamma I only need to know the configuration of sensors within a subset small gamma I. And so this expression is distributed over the neighborhoods gamma i's. These neighborhoods can be overlapping. The nice thing is here the number of terms is n, where n is the number of sensors, not exponential in n. So now what we need is an algorithm to optimize this expression.
Well, It's true that it's linear in n, but for each setting of pentel zoom across all the cameras, right, all those regions will change.
Right. So the subset gamma I depends on not just one pose of the sensor, but all the different poses of the sensor.
It's not really differentiable because you can have. I mean, it's not smooth, right? Because I mean, you could easily have one region could appear and disappear. Basically.
Right. So we are not making any assumptions on continuity or smoothness here. So these subsets gamma I basically depend on the locations of the sensors, and if each sensor knows its location, it can compute to what range the sensors can influence, and a worst case estimate of that subset gamma I is the number of sensors within 2 times the detection range with the zoom. So of course one could compute maybe a more efficient subset gamma I if one has exact knowledge of the obstacle, but if one doesn't, that is at least one estimate of the subset gamma I, and I will show my algorithm will work even if we have some extra sensors within the subset gamma I. So here's the algorithm. The same region that we were just talking about, where the region from all the poses of the sensor with which any other sensor has an interference, again from any of its poses, any of its span, tilt and zoom settings. Let me denote that by Vi, and hence based on that I can calculate this subset gamma I. We just discussed this. Now if a sensor I knows the pose chosen by any sensor in this subset gamma I, it can compute that subregion capital gamma I where it is responsible. So what I'm doing here is describing a heuristic used for optimizing that this metric, which goes like this. When a sensor I is deciding its pose, all other sensors within the subset gamma I, all other sensors which can potentially influence with the sensor, interfere with the sensor, will stay static. Only sensor I will move. And sensor I, of course, here is assumed to know what pan, tilt and zoom position has been chosen by the other sensor within the subset gamma I. And here's where the heuristic part comes in. The sensor I will choose a pan setting by searching only along the pan dimension, say. So it's a one-dimensional search along the pan settings. After having chosen the pan setting, it will choose among all its zoom settings, and so on for the tilt. The reason why this is a heuristic is I'm not searching over the entire possible combination of pan, tilt and zoom settings, so which is why I'm calling it a line search. Let's just visualize this for a simple case. Let's say we have just 2 cameras mounted on 2 diagonally opposite corners of this rectangle that we want to cover. This light gray region shows the coverage, the detection area for each camera. The shading is showing the detection quality. These white little thingies are obstacles which block line of sight and hence affect coverage. Each camera can choose a pan position between, say, 0 and 90 degrees. It can, of course, look in other dimensions, but that will be totally useless. So let's say we ignore tilt and zoom for now, just to get 2 variables so I can draw a graph on this 2D surface. So let's say this is the configuration. Sensor 1 can choose between 0 and 90 degrees. Sensor 2 can choose between 0 and 90 degrees. So what will happen according to the ILS algorithm that I just described? First, say sensor 1 decides to move, then sensor 2 has to stay static when sensor 1 is moving. It will search along all its pan positions. This graph here shows the utility metric for all the combinations of pan positions of the 2 cameras. Of course, this is never evaluated in the algorithm. I'm just showing it here for the purpose of illustration, calculated centrally. This was just 2 cameras, I can do that. So say sensor 1 will choose some angle where along this line, along its pan settings, this metric is optimized. So it will probably stop at this point. This looks the highest along this dimension. Then sensor 2 will move. It will search only along this line, its pan settings, where camera 1 had already stopped. So it will probably stop at this point. This is the highest point along this line. Then again camera 1 will move. It will stop at this point, and after this point the algorithm will terminate. I haven't described how the algorithm terminates, and it just so happens that in this particular example we are reaching the global optimum. I haven't proved that it will always reach the global optimum. So this is just a visualization why I'm calling it an incremental line search. Now I have a proof which shows that this algorithm will always cause the configuration to converge to a stable state. This is nice because we don't want the configuration to keep fluctuating. We want it to converge to a particular state. And in distributed robotics, that is typically the key thing that they prove for any algorithm for controlling the motion. This is still not proving that it's the global optimum, the state that we are converging to. We'll talk about that later on. So this is one key good property, and this is good because we have not made any assumptions on the continuity or the differentiability of our optimization metric. We have used the line of sight data as it comes from the lasers, but we can still prove this. And even the termination condition, which I'll just show, is a distributed one. We don't need a global node to know what the value of the metric is when the termination occurs. So why this particular heuristic, and why not some known optimization heuristic used for NP-hard problems? Say, for instance, simulated annealing. Reason one, there are no distributed versions available. Reason two, question?
I have a question about the last slide. If you have a plateau,
Yeah.
how do you break the tie?
Oh, so along this line, say, for instance, there was a plateau, then it will have to choose any point randomly. When that occurs in any incremental optimization algorithm, some of them can get stuck in the plateau, and then they just have to choose one random point, and that can affect where the next step of the algorithm will lead to.
Would that affect the stability of the...
No, that will not affect the stability for my algorithm at least. It might in some cases for some other algorithms, but for the ILS algorithm that I just described, choosing any point is fine. It will not affect the stability. So this proof holds. Okay, so I already talked about why not simulated annealing. That's one of the key heuristics, one of the main heuristics used. Another one is incremental subgradient descent. This is, the algorithm I described is also incremental in that we are searching along one line at a time, but it is different from incremental subgradient descent because that algorithm requires the optimization metric to be differentiable. In that algorithm, we compute the derivative along one variable at a time and optimize along that variable. It's a different algorithm, of course, and it cannot be used for this metric because one, my metric is not differentiable. Two, there's no distributed version of this algorithm. So, okay, up to this point, I just described the algorithm making certain assumptions. Question?
I would argue, and I can see based on other algorithms why your algorithm is globally convergent with holding everything constant and changing one. But in the distributed form, unless you make sure that nothing else is changing while you change one, that's not going to be, like if they can all change simultaneously, that's not really going to be true.
Well, let me repeat what I said, that when one sensor is moving, all sensors within a subset gamma I stay static.
So not just in terms of finding the best configuration, but literally you lock all the other...
Right. Because when one sensor is doing the computation, others do not.
And I guess in terms of like, I mean, it can still be distributed.
Yeah, because these other sensors in other subsets, not in this gamma I, can be moving, and these subsets can be overlapping. Is that what you were asking?
Oh, within that subset.
So not all the n sensors have to stay static, because then that would be a very slow algorithm.
Wouldn't they have to be in? But like even if one set was non-intersecting with a different set, but if there were sets in common that they had.
Oh, yeah, those can move. As long as when a sensor is, let's say there are two sets which are overlapping, say sensor 1 overlaps with sensor 2, sensor 2 overlaps with sensor 3, then when sensor 2 is moving, both 1 and 3 have to stay static, but when 1 is moving, 3 need not stay static. Okay. So, yeah, so one of the assumptions I made was this particular one, that when sensor I is moving, all the others stay static. So to achieve that in practice, what I have is a contention-based protocol, something similar to the RTS, CTS used in wireless networks, but not exactly, because one, we don't need the network here to be wireless. It could be wired or wireless. Two, it is not based on the communication interference. It is based on the subset gamma I that I described. So this contention protocol makes sure that at any given time only one sensor is moving. It does not make sure that there is a particular ordering to the sequence in which the sensors move, or even if one particular sensor moves more than the others. And the convergence proof holds regardless of these. To the term question?
They may or may not converge to the same point.
Yeah, exactly. Which is what when I described the proof, I said they converge to a stable configuration. It is not the global optimum. It need not be the global optimum. It could be. So, okay, and I'll come to that. The other thing which I did not describe in the algorithm was the termination condition. The termination condition is also distributed. It's like this. For each sensor, it will not actuate if it will not move, that is, change its pan tilt and zoom setting from the current one, if the incremental gain in the utility metric, that is the portion of the utility metric being computed by that sensor, is not above a certain threshold. So as soon as that threshold is not being met, this camera will stop doing the motion part. Of course, this does not mean that all the cameras in the network have stopped, and this does not even mean that this camera will not move at some point in the future. But the convergence proof holds in spite of this, and what that means is at some point, even though the cameras may not know individually, the entire network will become static. Different cameras may become static at different points, one may become static, move again a little bit, and so on. So that's the distributed termination condition. It's nice because we don't need a single central entity to know the utility metric. Third part, the event distribution, which I said that the network may know which regions in its covered area have more events happening. That can also be learned in a distributed manner. That is, each camera only needs to learn the events within the space it influences. That is, within the space it can access from any of its pan tilt and zoom settings. And that event distribution, essentially a histogram built up by detecting the events, need not be normalized over the entire network. It only needs to be normalized by that camera over its space over which it is measuring, over which it is detecting from any of its pan tilt and zoom settings, which means that building up this distribution only requires coordination between, say, that camera and others within its subset gamma I, not the entire network. So again, one other way in which the algorithm is totally distributed. Question?
It's something in the distributed termination. Do you have a global termination condition?
No, the condition is distributed.
So nobody knows whether...
Nobody knows when the network has stopped actuating. One camera might have stopped actuating, but others in other subsets.
When do you start to monitor?
Oh, they are always monitoring. So as soon as I start monitoring. It just means that at that point, I'm not having the optimal monitoring performance. At the point when all the cameras have stopped, it's the optimal reachable by this algorithm, that optimal monitoring performance. No camera will know when that actually starts, because we don't have a central entity which knows the utility metric for the entire network. So just to illustrate for a particular configuration, let's say this blue thing, these are the cameras. This is the starting configuration, and we run ILS, the algorithm that I just described. This is what will happen. This is how the utility metric will evolve. This is the global utility metric, which the cameras don't know. I just have plotted it from a central perspective. So now coming to evaluating this algorithm, is it a good one? First part, whether it converges, yes, that can be proved analytically. And that is proved in spite of all the realistic assumptions that we are making, that the utility metric itself has nonlinear terms, discontinuous terms. It need not be differentiable at all. Other two issues, is it converging to the global optimum? Like, what's the state that we converge to? Is it a good one or is it a bad one? Second, is it fast? Is it converging fast enough? Now, these two things are not easy to analyze in theory, so what I'll do is simulate these things and see what we can see from the simulations. So the first part about whether it's a global optimum. What I did was, and this is a suggestion, this is not a proof, this is just a simulation which suggests that it is close to a global optimum. What I've done here is ran this algorithm multiple times, starting from random configurations for the cameras and choosing different search paths. That is, in the distributed protocol that I mentioned, which the contention protocol, which causes the cameras within a subset gamma I to stay static and only one camera moves. Different contention success patterns are possible. Different cameras may win it in different orders, and I just simulated it for those different random search paths in the search space. And for each of those paths, we see that these are converging within about 10% of each other. This suggests, does not prove, that this is close to a good global optimum. And at least the nice thing that we can see from this graph is, if we were to not use ILS and let each camera optimize its own configuration based on what it knows about the environment, we would have gotten, in this particular in the same setting where I did these runs, we would have gotten this utility. And we are way above that particular utility using ILS. So that's one thing. The time question?
This is going back a little bit, and I'm still a little bit stuck on this. So let's consider the following example. Let's say you're in the midst of doing the optimization, and so you have these particular cliques of nodes.
Right.
And this one is initially separate from this one, so they're allowed to move at the same time. But in the process of adjusting this one's...
Oh no, these cliques do not change in the process of adjusting, because the way these cliques are defined is, for a sensor I, the number of cameras which belong to its clique gamma I are all those cameras which can interfere with it from any possible pan and tilt position. Yeah, exactly.
It's just impossible for this one to ever...
Right.
Okay,
yeah, as long as the locations don't change, these cliques don't change.
Yeah, you're good. All right.
So if the cliques change, the convergence proof will break down.
Yes.
So yeah, this was about convergence, how good the convergence is. Second is the convergence time. Question?
Go back to the convergence.
Oh, okay. Well, I didn't show the proof at all. It was just a...
Well, the thing that looked like an ROC curve that had all the blue lines converging to within 10.9% of each other.
Oh,
The slide you were just showing.
Yeah. That one. So on this one, you didn't compute what the global optimum is.
Yeah, because that is NP hard to compute for any realistic number of cameras. For the 2-camera case, I showed that figure where we did compute the global optimum, and ILS just for that particular case happened to reach the global optimum.
And how many cameras are there?
This is 25 cameras across a 50 meter by 50 meter space, deployed randomly, but the pan, tilt, and zoom settings are chosen using the ILS algorithm.
How many runs?
Each curve is a separate run, so there are like 10 runs here. One can do this more times.
See like what the, how wide
the
actually
spread
is once
can
you
go,
actually
yeah.
run it for the outlier.
Yeah, that's an interesting thing.
Because the best case, man. I mean, like you think of them as as pulling from some weird distribution. I mean, you're probably pulling mostly from the center, and there's probably one or a few that are really good, and a few that are really really bad.
Possibly, yeah.
And so best case is not quite.
Yeah, so I mean, these are just the typical cases that I pulled off. It's not showing the entire distribution. Yeah. Any other questions at this point? So, okay, so the time for convergence. Here, again, this is a simulation. This is not a proof that this will be so fast. But what I observed was that in all these random runs, each camera gets a chance to actuate on an average 3 times. Of course, some cameras may actuate more, some may less. And actuating 3 times, the total time for convergence obviously depends on the size of the subset gamma I, because for that time others have to stay static. And each update here, each actuation step, which I said each camera has to do 3 times, is 4 seconds for the particular hardware and the network configuration I had, because this depends on the motion time, which as I showed earlier on was a second or so, and the time for the communication. Time for the communication depends on the number of cameras, how large subset gamma I is spread. Question?
Do you have to actually physically move the cameras to do this?
So this is a simulation, but
Right. But in real life, it seems like if you knew the parameters governing the cameras, would you have to run the motors at all? Couldn't you just run
we could just run it at the final step when they have computed their optimal configuration. Yeah, I mean, in a practical setting, that's what we will do.
Because they can't detect their own overlap, right?
Yeah. All we need to do is each camera compute its next position, communicate within the subset gamma I. Right.
Wait, I don't understand what the x-axis number there is. Because it's much larger than 3. It seems.
Right. So the x-axis here is the total number of iterations. So we had 25 cameras. We divide it by 25 in that particular overlap.
So 3 pose updates per camera is 75 iterations.
And so we see here about at this point everything seems to converge. And this convergence time is dependent on the density, that is the size of the subset gamma I, and not on the size of the network. So if the network was to grow very large, it need not grow. But if the network was to grow dense, then this time will grow.
Furthermore, when you say 75 iterations, some of those could have been happening in parallel if they're in
right. So this is the worst case.
So
this is the worst case estimate. Yeah, because exactly. So for 4 seconds and for 75 iterations, here it's a matter of minutes for the network to converge, which is in this particular application much smaller. A few minutes is much smaller time than it would take for the obstacles in the environment to change. Obstacles in an indoor environment would be things like the furniture or the pillars,
and it will also be less than the time it takes me to update the event distribution that I have. I'll need to learn at least, say, a few thousand events to build a distribution.
So you talked about the obstacles changing in the environment, but I haven't seen so far if you had a column or something in the middle of the space, what's the mechanism for even knowing about that there might
Oh yeah, so I didn't talk about it today. I just showed that I do it using lasers. I gave a reference. Yeah, I'll just show a picture of that too. So yeah, so this was evaluating it. Now, one other property which is nice about this algorithm is that it degrades gracefully if the environment is changing fast. And that happens because in the proof, I didn't go through the proof, but the way the proof works is that first we prove that the utility metric is increasing monotonically under the execution of ILS. What that means is if we change the environment before the algorithm converged, the metric would only have increased, but it might not have reached the best possible using ILS. So if the environment was to change faster and faster, the algorithm might be further and further away from its optimal that is going to reach, but it will always have only improved the utility. And depending on how slow the environment changes, it will increase the utility more and more. So that's a graceful degradation. It's not breaking down the algorithm totally. So we evaluated the algorithm, and finally I'll just show its implementation, proving that it's a realistic. We haven't made any assumptions which cannot be mapped to a system. This is a test bed. This has been demonstrated at Census and IPSN. We had 4 cameras, a bunch of fake obstacles, and 2 lasers, which mapped this environment from 2 corners. There was one here, one here. So, and there's a separate process controlling each camera. In this case, I just made a GUI for each process too to show the data it got from the lasers, mapped it on its 3D view to see where the obstacles are. And this is just for the experimentation purpose. This is what the laser data looks like. Scan from one corner, scan from the other corner. It can be combined to get the obstacle map. And this is what that particular configuration looks like. I mean, if we were to manually deploy the cameras in a regular tessellation thinking that it covers the entire space, the obstacles might cause it to not cover the entire space. And then if we were to run ILS, it will improve to a configuration where more of the space is covered. And this is for the actual test bed that I just showed. And what I'm trying to do now, and this is work in progress, not yet done, is do it for a more realistic application using motion detection to build a map of where the events occur. Say the application is that we want to keep a log of all the vehicles entering. This is the entrance to UCLA along Strathmore Drive. We want to keep a log of all the vehicles entering UCLA. And we want to take an image at a sufficiently high resolution where we can read something recognizable about the vehicle, say the number plate. So what we are doing here is using motion to detect these vehicles, and then the cameras will zoom in to take those pictures. And this is work in progress. The motion detection in an outdoor field has some issues which I'm working on. So what we did see today was, one, that small motion has a lot of promise. It can give a significant advantage in sensing performance. Then I showed a system architecture which allows exploiting the small motion capabilities and what are dependencies we have to use this. And finally, I, of course, described a distributed algorithm to configure the network that gives it a good configuration. Now, this was one direction in the general theme of improving the reliability of the network. And I think this is important in the general trend that we see sensors not being restricted anymore to just an industrial setting or a scientific lab setting, but being used in pervasive computing environments, in more unstructured environments. And hence, we trying to improve the reliability of these networks using, say, high-resolution data would definitely be an interesting issue. Another interesting issue which I've had some work in was processing the data that we get from the sensors, converting it to something which the user is interested in. That is, say the sensor is giving me accelerometer readings, RFID tag values. What the user wants to know is something more interesting. Say the user wants to know whether a product is delivered or which particular species is present in the environment, how many people are present. Converting the sensor data into these metrics of user interest is another problem which I see interesting in the sensor networking space. So with that, I'll end. Let me just say the projects that I mentioned, aside from the one I talked about in the beginning, I showed a few. Those are all in collaboration with a lot of other students. I'm not going to read all the names here, but I can give you references. and the details on those projects are available in these publications. And one other project which I didn't talk about was using energy harvesting. We can talk about it offline in individual meetings. This is showing a little picture of the prototype that we built. It's a sensor node which can harvest solar energy from the environment and use that for operating. Thank you. Question?
In your actual test, it looks like one element that wasn't in there was the probability of events happening at different locations.
Right. Yeah.
So that, why did you use that?
So as far as that test is concerned, we can do that in two ways. One is we can simulate an event distribution over that blue floor that I showed and feed parts of it to the different cameras, which is only, a simulation. It can be done easily, but I haven't just done it. A more interesting way would be to actually have some applications, say the tag application which I showed, where color detection is used to detect events, have those events occur at different points. That can definitely be done, but it's a harder thing to do. Just definitely that is one piece missing in evaluating that.
There could be other things. You could just know something. Like you could say that, like, for instance, like if it's a cafeteria,
right,
you might be able to say that this area is where people sit and this area is where people. Like you might be able to kind of lay out something, what a map of the event spaces might be.
Yeah. If we have some a priori information, that can definitely be fed into that QP, the metric which I showed. Otherwise, one would just assume a uniform distribution over the entire space.
You might want to look at just the inverse of that probability distribution, right? Because if you see someone, say, rappelling down the side of a building where you've never seen someone do that before, that's pretty important to see, rather than just a Volkswagen driving on a road where you don't see it.
Yeah, exactly. Depending on the application, if you are trying to detect like malicious users or atypical users, then looking at the inverse would be very interesting.
So one thing I would think of, I guess in the same line as thinking about a kind of a security kind of scenario, there might be things like, as opposed to maximize coverage, you might have constraints. Like, for instance, holes might be really bad.
Hiding spots would be really good.
And have you thought about being able to have constraints like that, to be able to say that, like, I definitely want, within this region, no holes or something like that?
Yeah, the one way to model that is we give low priority, lower weight in the linear weight to the delay.
QP to push it, but it wouldn't guarantee.
Yeah, this algorithm is not guaranteeing, but it is able to show us, if we know the obstacle map from the given configuration, we can compute the holes. So at least it tells us there are holes, while that is at least a step towards guarantee. Guaranteeing might not be possible with the given number of sensors. It might have to tell us that, okay, you need to deploy more.
That's true, but that might be a reasonable answer to give. It might be to say that, like, okay, we can cover this area without holes, but we need, one more sensor.
Yeah. So this algorithm will at least tell us the holes. It won't tell us how many more sensors we need.
Is there anything fundamental to your algorithm that wouldn't let you optimize for the XYZ placement of the cameras?
As long as the utility metric can be written in the distributed manner, it can be used for any other optimization. But for the placement,
the clicks would change.
The placement, the clicks will change. It's not a
big piece.
And there is a lot of work for the deployment problem itself, the art gallery problem.
It wouldn't. I guess the thing that would happen is that basically your distributed algorithm would essentially become serial.
Right.
The whole thing would be one big clique, and you just have to keep everything solid except for one, and so it'd just be slower.
So it will solve it, but there might be the other algorithms available for that problem might be better.
That too.
Like if it takes half an hour to go through everything.
That's true. Well, except that it doesn't actually have to move in order to do the algorithm.
Right.
So,
That's a much older, much more looked at problem, the problem of deploying these things. So there are algorithms, centralized ones and some distributed ones too.